Yeah, okay. Whatever I am going to say, of course, has not been covered earlier. Otherwise, I would not be giving this lecture. But on the other hand, if you take each part, each piece of what I am going to do, each piece has been already covered. And therefore, that makes the life a little easier to really go through the thing quickly. And whatever I say is very well explained in the book of Iwani, and therefore, I mean, I would urge you to read that. And therefore, I am not going to do everything. I am just going to explain some basic ideas from that proof where you might have difficulties or things related to whatever that is there. And that's all I am planning to do. Okay. Therefore, we start with what is called delta. This is something which has been defined in the lectures by Rita Pratha, namely that this is a number which is equal to 1 if n equal to 0, and 0 if n is not equal to 0. And the whole idea is essentially to explain, to simplify this complicated function into something simpler. Okay? And Rita Pratha was also mentioning about the Kloosterman's delta n, which he did not prove and which he did not use. And the reason why he did not use is that the parameters cannot be from the analytic part and the arithmetic part cannot be so easily separated. And now there are other versions where they can be separated, they would be much better. But for my purpose, which is the application of delta method for a certain problem, Baring's problem, okay, this is not bad enough, and that's exactly what we are going to do. Therefore, there are two things, delta method as well as Baring's problem. Delta method also has been covered, Baring's problem also has been covered, and we are going to combine. Okay, therefore now let's start with this delta and write the Kloosterman's delta function and try to prove it first. One function which we already know to write the delta n is equal to 0 to 1 e nx dx. This is where we normally start with. And then this we want to write down, and preferably into the major arc, minor arc, and then do the things. And therefore now let's define the major arc. And the major arc, as all of you would have probably expected, would have known, is coming from Faraday fractions. Okay? And the Faraday fractions is at least all of you know, but let me just go through quickly because there is one important point which I need. For example, take the Faraday fraction F5, which is what? 0, 1 over 5, 1 over 4, 1 over 3, 2 over 5, 1 by 2, 2 by 3, 3 by 4, 4 by 5, 1 by 1. That's a Faraday fraction. And Faraday, who was not a mathematician, who was a surveyor, land measurer, and so on and so forth. Oh, yeah, sorry. Yeah, here it is a 3 over 5, and then there's a 2 over 3, and then there's a 3 over 4, 1 over 4 over 5, and 1 over 1. And you made some simple observations. And the simple observations are that if A1 by C1 and A2 by C2 are consecutive, then A2 C1 minus A1 C2 equal to 1, which always happens here. This is 1, and this is 1, and yeah, and this is 1, and so on and so forth. And remember, yeah, this is one thing. And the second thing which he had is, of course, most of us would have some experience in our high school when we were learning fractions first, and always when you have to add two fractions, adding the numerator and adding the denominator. And therefore, if you do such a wrong divisions, then if you have 3 consecutive ones, then the middle one will be exactly the addition of the extreme ones in the wrong addition, if I do that. Okay? For example, if this is 2 by 3, then this is, okay, I'll take another example. 3 by 5, then 1 plus 2 by 2 plus 3 is this 3 by 5. Okay? And remember, when we do the wrong addition, you need not get a fraction in the reduced way. It need not even be reduced. For example, now, this is the example I started with. This one, 3 by 5 and 3 by 4, if I do the wrong addition, I get 6 by 9, which is not reduced, but which is equal to 2 over 3. Okay? These are the things probably you know. And there is one thing which I'm not sure how many know is, okay, anyway, then once you have that, and then there is something called the median. And this part around A over C, you take the median to the left, median to the right, and that part you take, and that part will be the major arc. Therefore, this major arc would be this part, which is A plus A dash by C plus C dash, and A plus A double dash by C plus C double dash. That will be the major arc around A over C. Okay? And I need something about this major arc. Therefore, let me write out that. The same notation is what I will be using. Now, this is over this major arc is what I am going to integrate. If I am going to integrate over this major arc, I should know what is the length of this major arc. Okay? Therefore, each part I can take separately. Look at this part, this length. Okay, what is this length? And that was a comment which was made by Professor Deshwe on his lectures on Tuesday, namely that this distance, which a priori looks as a parameter on 4 variables, A, C, A dash, C dash, is really a function of 2 variables, A and C alone. Okay, and this A dash and C dash can be made to disappear. Okay, how many of you have seen that proof of that fact, that A dash and C dash can be made to disappear? Up to C. Yeah, oh, yeah, exactly. There is another problem which I found in this, when reading a mnemonic book, he is using C and capital C, but when you are explaining on the blackboard, it's little difficult. I will try my best to see what is the C and what is the capital C. I wanted to change the notation, but on the other hand, I thought most of you would be learning it from the book of mnemonic, and therefore it's probably not a good idea. Okay, therefore that's a statement which I now want to prove. Okay, therefore now what is the distance between that's what I am interested, and I would like to know that this depends only upon A and C, and somehow it doesn't depend upon the A dash and C dash in some sense. Is it okay? Let's simplify this. For technical reason, the C plus C dash I will call D dash from now onwards. Okay. And now you see this A dash by C dash and A by C are consecutive ones in FC. Since A dash by C dash and AC are consecutive ones in FC, then you know AC dash minus A dash C equal to 1. Therefore, that is the distance. Therefore, some variables have gone, but there's a d dash which has suddenly come. And now the question is, what is it I know about d dash? You say, okay, therefore let me see, what do I know about d dash? One thing is that this element did not appear in the Faraday fraction for Fc. Okay. Since this element did not, but the Faraday fraction Fc consisting of all fractions whose denominators are less than or equal to C. Therefore, the very fact that this element did not occur means that the denominator C plus C dash should be bigger than capital C. Therefore, oh God. Therefore, the first thing which I know is this denominator is bigger than capital C. It's okay? Okay, there's a lower bound. Now let's look at an upper bound. Now you see, this C dash is less than capital C because the C dash appeared as a denominator. Since it appeared as a denominator, C dash is less than capital C, and therefore this C plus C dash is less than little c plus capital C. That is one information which I know. Okay? Now let's see what is the other information which I know. I know again I go back to this and I know that AC dash minus A dash C equal to 1, which essentially means, yeah, AC dash minus, which essentially means that this AC dash equal to 1 mod C, and therefore this C dash equal to A bar mod C. Okay, now let me make one remark that throughout the lectures, the bar stands for inverse mod C. Okay, and therefore C dash is A bar mod C. Oh God, let me. Let me put it off. That's much easier. And that would mean that C plus C dash is also A bar mod C. If C dash is A bar mod C, a C plus C dash is also, that would essentially mean that D dash equal to A bar mod C. Therefore, what do I know about D dash? D dash is in a specific residue class modulo C, and D dash lies in a specific interval of length C. Then if you have some element which runs in a specific interval of length C and equivalent to a specific number modulo C, that number is essentially determined by the other parameters. You don't need anything more. Perfect? And therefore, this D dash is something which I know. And the distance is 1 over CD dash. And therefore, the distance is only as a function of A and C. Nothing more than that. Is it okay? Good. And now we go. Therefore, now this is equal to integral arcs 0 less than or equal to A less than C, AC congruent to A and C equal to 1, and C less than or equal to capital C. That's all what you have got. Okay? Now you would probably, sorry, E of nx, yeah, nx, the same thing. Same thing, 0 to 1 I have broken, that's all. 0 to 1 I have broken, okay? And this is, Ionic has other applications in mind. Instead of looking at it, he looks at a general function f of x, which is periodic mod 1. Satisfying the extra condition that f of minus x is equal to f bar x. And your function Enx satisfies both these conditions, and we will manage with the f of x. Sorry? Sorry, here bar is complex conjugate. Yeah, I think you have to understand everything from the context. This bar is, of course, a complex conjugate. And therefore, consequently, we have the summation 0 less than or equal to a less than or equal to c, ac equal to 1, c less than or equal to 1 less than or equal to c less than or equal to capital C, 0 to 1, f of x dx. No, MAQ, MAC, f of x dx. Okay, which now we can simplify that 0 less than or equal to a less than or equal to c, ac equal to 1. I will not be writing all the conditions again and again. 1 less than or equal to c less than or equal to capital C. Integral f of a over c minus, remember the integral is from this particular point to this particular point. And for this particular point, we have even got another formula, namely a over c minus the distance. Therefore, this point can be written as a over c minus distance. And the distance also we have already written cd dash. And this d dash is equal to c prime, c plus c prime. Taking everything into account, this is minus 1 over cd dash to 1 over cd double dash, which you know what it is. cd double dash being, of course, d double dash being this length, and d double dash is c plus c double dash. Okay? This is okay.
There is a slight different definition of M0 and M1. M0 starts at 0.
Yeah, that is true. Okay, yeah, exactly. Those things I slightly ignore because at the end points, of course, you won't get the full interval at the end, and those things I am just ignoring. Yes. And therefore, consequently, this is 0 less than or equal to a less than c, ac equal to 1, 1 less than or equal to c less than or equal to c, minus 1 over cd dash to 0, f of ac plus x dx plus 0 to 1 over cd double dash f of ac plus x dx. Okay? Now you see in the first integral, there are 3 variables floating around, a, c, and d dash. Okay? But on the other hand, we said already the d dash is in terms of a and c. Okay? But now instead of that, I am going to say that a can be written in terms of d dash and c. Therefore, a I am going to forget, and d dash and c I am going to keep. Therefore, that's this condition is gone. This condition is replaced by little c less than or equal to d dash less than or equal to c plus capital C. That's the one which we got for d dash. Little c less than or equal to d dash. And this a, this d dash was an inverse of a modulo c. That means this a is the inverse of d dash modulo c. And therefore, this is d dash. Okay. Now, therefore, instead of two variables, instead of the 3 variables, I have made 2 variables. Okay. First introduces the D. I started with the A and C, introduces the D dash, and then use the D dash to eliminate the A. Is it okay? Once I do all those things, there is no point in doing D dash and blah, blah. It's difficult to write. I'll call it D. Now we'll come to that. No. This is one sum, and now this is second sum. The second sum, this A is minus D double dash. Okay? Bar. It's a minus D double dash bar because when you now look at it, you will get A times D double dash will be equal to minus 1. We'll do the same argument, whatever we did for the first part. And therefore, there will be minus D double dash C. And then once I do that, I don't need to have this double dash. I mean, I take separately the first part and second part and throw away all this funny D dash, etc. That's exactly what I have. And now let's simplify this. Now, therefore, there are only 2 variables now. Okay? Oh, C and D. The A is the one which I didn't like to throw it away. And now, obviously, I can make a change of variable. And the second one is okay. And now this is something which I want to simplify. And now you observe that this particular number is the negative of this particular number. And that's why I made an assumption about the negative, that the negative is the same as a conjugate. And therefore, now I can add both. Then I get the conjugate, and that gives you a certain thing which I will need again and again, and therefore let me write it separately. This is what Ivani calls mu of f for a general f is equal to 2 times the real part of summation 1 less than or equal to C less than or equal to capital C, C less than or equal to D less than or equal to C plus capital C, if you integrate 0 to 1 to C over D, f of d bar minus x dx. Sorry? Yeah, little c is smaller than capital C. Oh, yeah. D is no, D is between little c and C plus capital C, so that it will be the neutral with capital C. Yeah. Yeah. Capital C to C plus capital C, so that it lies in a neutral with C, and it is determined with respect to modulo C. Oh yeah. Therefore, there will always be a star. Okay, the star always standing for the coprimality. Is it okay? This is the starting point. Now I have to derive what Munshi called as the Kloosterman identity. Therefore, let me do the Kloosterman identity. First of all, in this particular thing, I make the change of variable x is equal to y over cd. That gives you mu of s equal to 2 times the real part of summation over little c and little d. I won't write that. And then you will get a 0 to 1. And then you will get a f of d bar by c minus x y over cd dy. And there will be a 1 over cd floating around. Ready? Sure, sorry. I thought I was already doing that, but unfortunately, over cd dy. Okay. In particular, taking f is equal to f of x is equal to e and x, then you get delta n equal to, this is another formula which I want. Therefore, you get delta n is equal to 2 times the real part of summation over cd under those conditions, 1 over cd into integral 0 to 1 f of, no, e of n d bar by c minus n into y over cd times dy. Okay, that's exactly what is called Kloosterman's delta function in this particular. Is it okay? Since Kloosterman is used in many places, and therefore consequently there should be other ways of writing it also, and therefore let's try to write it in a one different way. And the other way I want to write it is essentially I even go to the mu of f is equal to 2 times the real part of summation. The first form I take, the summation is over CD star, of course, and then you have an integral 0 to CD, 1 over CD, f of d bar by c minus x dx. And the first thing which I really plan to do is to bring the d inside. Okay, the d inside, how will that change? Therefore, this is equal to 2 times the real part of summation 1 less than or equal to c less than or equal to capital C. The d I am going to take inside, and therefore there will be this also. And then I will take the d inside, and then I will have a f of d bar over c minus x dx. Now I have to write the conditions on d. And one thing is that already we know that the capital C less than or equal to d less than or equal to the little c plus capital C. The other condition on d was that this funny thing, which means that you have a 0 less than or equal to x less than or equal to 1 over cd. And then condition will go now have to be translated into d, and therefore consequently d is less than or equal to cx. And the interval will be of all the possibilities, the one which is the highest interval is that what will come. And since your d is bigger than or is equal to capital C, and therefore this number will be 0 to 1 over little c capital C. Ready? D is less than 1 over, 1 over cx. That's the condition that you will get. Is it okay? Let me check. Just check whether I have done no goofing so far. Let us simplify this. And I don't like this 1 over Cx. And therefore, now let me make a change of variable 1 over Cx is equal to y. And then this number will become 2 times the real part of summation 1 less than or equal to C less than or equal to capital C. Now capital C to infinity, summation over D, f of d bar by C minus x dx. And of course, the summation over D, now the summation over C, D is C less than or equal to D less than or equal to C plus little capital C. And also extra will be D less than or equal to Y. And dx by x square. And there will be C. Where will be the C is 1 over d. Okay, therefore dx will be is equal to 1 over C dy by y square. Okay, let me change up. Now, what did I do? Yeah, 1 by Cx is what I changed it to y. And therefore, this will be x will be changed to be 1 over Cy. And dx will give you a dy by y square. And dy also will give you a 1 over C. Dx is equal to 1 over C dy by y square. Thereby, there will be a 1 over C. One minute. Did I have a CD earlier? No, not in this. It's okay? 2 times the real part of 1 less than or equal to C, 1 over C into integral part of D. Let me just check whether I have written it correctly. Yeah, that seems to be fine. Now I want to look at this particular sum. And this sum, my problem is that there is an extra D less than or equal to Y. And I would like to complete the sum. Since I would like to complete the sum, that's yeah. I would now like to complete the sum, but how do I do that? Again, use another delta. That's all. Oh, this I need. Therefore, write that summation, the inside summation, as summation over D, C less than or capital C less than or equal to D less than or equal to capital C plus little c. And then you have an f of d bar by C minus 1 over Cx into g of x comma d dx. This g of x comma d which I have put is essentially another delta function, and this number is equal to 1 if d is less than or equal to x, 0 else. Because I have this condition d less than or equal to x, and I throw away the condition d less than or equal to x by introducing another function g of xd. Sorry? Dx by x square. Okay. I just have the same condition d less than or equal to c less than or equal to c plus d, and this particular condition d less than or equal to y I want to forget. And since I want to forget the condition d less than or equal to y, I should do that. I mean, y I am calling x, and d less than or equal to x I have to forget. And therefore, that I forget the condition by saying introducing another function g, which is equal to 1 if d is less than or equal to x, and 0 otherwise. Sorry? No, interesting. It comes from the change of variable. Well, first of all, I should know how to simplify that. Is that what you mean? Yes. Dx by x square has no point. Yeah. This is something which I want to simplify. Okay? Now, how do you simplify that? Which means I need a formula for this g of x. What's the time now? Crossing? Okay. We started a little bit later. Okay. Now, for this g of xd, I need a formula. I claim one can take g of xd to be minimum of 1 and the fractional part of x minus little c by c, and then minus d minus c by c. Is that what I'm getting? Something like that. Anyway, c minus, no, x minus d by c, c minus d by c. This will give you exactly a formula for g of xd is what I want to claim. Okay. Let us look at that. First of all, you see your d is much bigger than c. Therefore, this c minus d by c is a number, negative number, which is little less than 0. And therefore, this integral part gives you minus 1. But as far as this part is concerned, if x is, if x is bigger than d, this will give you, of course, plus 1. Therefore, 1 minus 0. But otherwise, if x is less than d, then this also will be little negative, and that will also give a 0, and this will give a 0. Good. Therefore, the g of xd is a nice function, and this function you can try to do. Is it okay? Good. And therefore, let us assume that I have put this g of xd here. And then I want to know what is this g of xd doing. Is it okay? Therefore, the g, one can take this function as the g of xd because this function is equal to 1 if d is less than or equal to x and 0 else. Okay, so that I can complete the function. I don't need this extra condition. Is it okay? Now, I claim again that if x is bigger than or equal to little c plus capital C, then g of xd equal to 1. Okay. And that is again obvious because if the x is very large, then of course this minimum already will be 1. Is it okay? No, what is that? D is bigger than, no.
X is greater than equal
Yeah.
to
It's greater than or equal to D, and that's all I need. And therefore, this is something which I will write for some technical reason. Minimum of 1 minus x minus c by c, because when the x is bigger than or equal to c by c, then of course this is the minimum is 1. The reason essentially is therefore, therefore roughly speaking, my g function is a very nice function if x is bigger than or equal to little c plus capital C, and somewhat a weird function if capital C less than or equal to x less than or equal to capital C plus c. And I need all those essentially because this is what I have to integrate. I have to integrate c to infinity. Let's recall the integral which we needed is c to infinity summation over d and dx by x square. Okay. Therefore, for c, x bigger than or equal to c plus capital C, it gives you a nice value. Now for capital C less than or equal to x less than or equal to C plus C, what to do? Is a question. Good. Now therefore, now let me take a detour and introduce you something else. Introduce you something else, what are called the psi function. Okay. How many of you have handled the psi function, doing some work where you have the psi function and you have estimated it? You only one you have handled it, psi function. And that's what I want to do, and therefore let me do that. Okay, what is this psi function doing? Okay. Therefore, what is the psi function doing? Therefore, let me start with an example. What is the psi function doing? And therefore, let me start with the divisor problem, which is a standard thing. And therefore, we are now interested in summation dn n not exceeding x. And I assume that most of you would know what is okay. One. This is the so-called hyperbola method of which I assume all of you know. Therefore, I am not going to explain. And then you are going to simplify this. When you are going to simplify this would give you an x over a. And when you do this x over a and sum over x over a, then you get an x into the logarithm of root x plus gamma plus O of 1 over x. But you don't even know how to handle that O of 1 over x, which means that most of the time you will have a sum. This is exactly the problem would be. Most of the time you will have a sum of something. And this x may not be an integer. Therefore, what you will do is up to mod x, and then you write the O term, and the O term will be O of 1, and O of 1 most often than not will kill you. Okay, and essentially because this O of 1 would be positive some other time, negative some other time, and you will have no idea at all where it is positive and how to use that cancellation. Good. And therefore, the best method is essentially to use the following formula. Because this being x minus integral part of x minus half. And therefore, this integral part you have written as a nice function with no integral part and whatnot, together with this psi function. And you know how this psi function looks like in the graph. Okay, this psi function looks like goes from minus half and goes up to plus half and stops there and come back and so on and so forth. Okay, therefore, this has both positive and negative values. This has positive and negative values. Therefore, when you sum over the psi function, of course, you expect enough cancellation. And therefore, you should know how to handle the psi function. One great advantage is that this function is a periodic. And therefore, it admits a Fourier series. Okay, and therefore, you can now write out the Fourier series. Sorry? Okay. Since I thought late, I started late, I thought I'll skip the break. But anyway, let's have a break. Yeah, probably it should be. Yeah. Sorry?
You tend to write like Sharma. She's very small.
No. Oh, I see. Okay, I'll make it still bigger. Yeah, we'll
Continue till 1.
Till what?
Because we started.
No, that's okay. No problem. I'll do instead of 12:45, I'll try to 12:50 or something like that. I'll tell you. Okay, the advantage of psi is essentially that it admits a Fourier series because it is periodic. And therefore, the periodic Fourier series I can write say 2 pi Ly. Which one? 2 will not be there? No, that's not will not matter. It's okay, I don't know. Anyway, the constant won't matter. Okay. Therefore, this will be the Fourier series, which I will normally write more up to a constant. Okay, I cannot use C for that. C I have used. Okay, I don't exactly remember what the constant is. That is e power OL by L. Okay, and that's all. Is it okay? And now one uses this whenever you have this problem, you one uses that and then estimate it. That helps us. And then one uses what is called the exponent pairs. And for example, in this particular problem, this would give you, for example, summation dn is equal to x log x plus 2 gamma minus 1x plus O of 1 plus summation plus O of 1 plus summation s less than or equal to square root of x psi of x over s. Is something which you can easily prove by everywhere writing that integral part and replacing the integral part by that number minus psi of y and then simplify. Everything nicely will boil down to this. And you say, if you just use the fact that psi is bounded, then of course you get the error term, which is O of square root of x. And that is exactly what Dirichlet did. Yes. But on the other hand, in psi, there is a change of the psi, there is a cancellation. Because psi is both positive and negative. And that cancellation you can use. Okay? And one of the ways of using such cancellations is what is called exponential sums and exponent pairs. And then when you use an exponential sum and an exponent pair, then of course you will get O of x for 1/3 plus epsilon. The epsilon also can be improved, but anyway, the improvements on this particular result is also known, but probably most of the improvements are probably in the second decimal place. Therefore, not really worth much. Is it okay? Therefore, this is how we use a psi. Now, the only thing, first of all, is that this funny thing is an infinite sum. And the infinite sums are little difficult to handle. Therefore, you should truncate it. Okay? Therefore, let's truncate it and see what happens. I claim that when you take the psi of y and truncate it, then if, for example, a times the fractional part of y is probably less than 10, then this gives you O of A times mod y inverse. Okay? How many of you can see a proof of that? Good. Okay, I will leave it as an exercise. Where to prove the summation. When I say ELY, I always mean sign, because I add L and minus L, because whatever I am saying more or less may not even be true for ELY if you add it in a different way. That's it. This is what you have to estimate. And such an estimate is what is called by Abel summation formula. If one of them is monotonic and other one is, has a partial sums bounded, then you can do that. And this 1 over L is monotonic, gives you a 1 over A. And the sign gives you a partial sums bounded by 1 over distance to the nearest integer. And therefore you get that. Is it okay? Okay. I assume all of you know what Abel's partial summation is. And in fact, if you want to do analytic number theory, that is the first thing which you have to learn. And therefore, if you have not known it, the first thing you have when you go home is to know what is Abel's partial summation. The next claim which I make, which is A modulo y is less than or equal to 10, then psi y is equal to summation sin 2 pi I Ly divided by L less than or equal to A plus O of 1. And that will not essentially come from Abel's partial summation, but on the other hand, here both the left hand side and right hand sides are O of 1, and therefore you cannot do anything more. This is, of course, a bounded function. And now you have a sin 2 pi Ly is bounded by Ly, and the L cancels. And then you have only A terms, and Y you are adding A times, that is AY, and AY I assume to be less than 1 over 10, and therefore there is O of 1. Therefore, essentially, you can break it at any A, and you get a good error term. And therefore, that's what we will do. And in fact, you can do a little better, as Professor Drishwe was mentioning in his lecture of the various systems of Waller. Waller also got an approximation to this psi of y by a finite Fourier series. And therefore, let me state that also, which is what we will be using again. That's a theorem due to Waller. There exists a psi star of x, okay, you fix an m first, and these coefficients will depend upon m. There exists a psi star x, which is a finite Fourier series, such that this psi of x minus psi star x is less than or equal to summation BMM EMX. Again, this goes only up to m, and this BMM is explicitly given as 1 over 2m plus 2 into 1 minus mod m by m plus 1. This BMM is known as a Fayer's kernel, etc., non-negative, etc. It has some nice, interesting properties. And further, these AMs will not be 1 over m, but at any case, AM of m will be less than 1 over m, which is good enough for your purpose. Therefore, there's a finite Fourier series whose coefficients are bounded by 1 over m, and you can approximate it, and then you take the difference. The difference is given me essentially by the fair kernel and so on. Therefore, this is also something which you can use. Is it okay? And now with all these things, let's go back to what we are trying to do. Put the dx by x square. As Professor this way pointed out, at that stage I need not put, now I have to put the dx by x square. And consequently, the integral which we are looking at is one over 2 pi I, sorry, there's no 2 pi I, integral capital C to infinity, summation, little c less than or equal to capital C, there's a 1 over C, and then you have a summation f of d bar by C minus 1 over Cx. No, this I have already made to be different. 1 over Cx into this by g of xd into dx by x square. That's the summation which I have. And this g of xd, which I have already written, equal to minimum of 1 comma integral part of x minus d by c minus integral part of c minus, integral part of c minus d by c, capital C minus d by c. And that's a function which I have to put, and I should know how this function behaves between c and infinity. And we just saw between c plus c to infinity, this function behaves well. It is equal to 1. Okay? And at around less than that, it should behave essentially like x over d minus c over d minus c plus your psi functions. Okay, that's why I said that between c and c plus c plus c, it behaves rather weird. You have a main term which is x minus c by divided by little c, but on the other hand, there's also the extra psi functions which are floating around. Is it okay? Given that, we can now simplify this. Therefore, let me simplify this x integral. Therefore, this integral, I am now going to break it into two parts, c to c plus c. And in this particular part, then I have a c less than or equal to c, 1 over c, and then you have a summation f of d bar by c minus 1 over cx times 1, because in this particular case, I have no problem, dx by x square is 1. Oh, sorry, you are absolutely right. Because that is a point where function is equal to 1 plus this c to c plus c. Then again, I have a c less than or equal to capital C, 1 over c, summation f of d bar by c minus 1 over cx into, in this case, this is funny thing, which is x minus c, capital C, divided by little c, plus psi of x minus d by little c, minus psi of capital C minus d by little c. Oh, okay. C to capital C plus C. Okay? Therefore, in this particular part, there is a main term which is x minus C by C. And in that particular part, there is a 1. There's a minimum 1 also. That's what I get. Okay? Dx over times the dx over x square. And now in this particular part, if I now replace this one by minimum of 1 comma x minus capital C divided by little c, which I am allowed to, then the main term turns out to be same in both the integrals. Because in the second integral, it is minimum of 1 minus x over c by c, and therefore the one also I can replace by minimum of x over c, and therefore that essentially will give you and then I can combine both the integral. Therefore, I will get c to infinity, capital C to infinity. Then I can, of course, put the inside the c inside or outside. It doesn't matter. 1 over c. And then you have a summation f of d bar by c minus 1 over cx into minimum of 1 and capital C, x minus capital C divided by little c. That's the one which will come everywhere times dx by x square. And then there is another integral capital C to c plus capital C. This integral, you will also have the same thing, etc. This is psi functions protocol. The main term can be written and separately the other error term will come. And in most of the application, of course, this will be the main term. And the psi function will give you the error term as to be expected. In fact, I can even write this summation d mod c psi of x minus d by c minus psi of capital C minus reciprocism E of n. Okay, now let's take the special case. The special case in which we are interested is f of x equal to E and x. Now let's take f of x equal to E and x. And here it is a summation is d mod c. And the summation is with a star. Of course, d and c co-prime. And once it's d mod c, it doesn't really matter. I can as well put a d here, f of d by c, because that d and d bar, it makes no difference. When d goes over the mod c, d bar over. And then I can simplify that funny thing. And that funny thing is called summation. The first term, d mod c, E of nd by c into E of minus n over Cx. That summation is what we want to do. Okay, now the question is, how do you do this summation? Okay. This summation is called a Ramanujan sum. And then we want to see what is this Ramanujan, how to do it. Is it okay? Therefore, now that takes us to the next chapter. What is the Ramanujan sum? Which is what is coming there. For any q, you look at the sum E of n A over q, n mod q, and A and q are co-prime, and n and q are co-prime. That's the sum which we are want to look at. And for example, if n equal to 1, then this sum essentially runs over all the primitive qth root of unity. And this particular sum is called the CQ of n. Summation over A mod q. Okay. Therefore, in particular, n equal to 1, for example, then it is really going through all the primitive roots of mod q. Is that okay? This sum is known to be Ramanujan sum, and then one should like to know how do you do this summation. Okay, this is again an exercise because this lecture is not on Ramanujan sum. Therefore, I will take the results for granted. And the result is that this CQ of n is equal to summation d dividing q, d dividing n, u of q by d times d. Okay, one easy way of proving it is that this funny thing may not be multiplicative in n, but this is multiplicative in q. And therefore, you can reduce to the case of prime powers, because whenever you have a multiplicative function, you can always reduce them to the case of prime powers and then do the things, etc. Okay? And remember that if these funny things were not there, okay, then that number is nothing but phi n. Out of this, you have this extra one. That's all. Okay? Therefore, this is what is called as the Ramanujan sum. And this Ramanujan sum has many properties. And again, as I was telling about the things, I mean, without Ramanujan sum, you cannot do analytic number theory. And therefore, if you have not seen Ramanujan sum, again, this is one thing which you should. And therefore, you can, once you have this particular formula, it is always possible that you would be able to write the CQ of n and simplify it, what is CQ of p power alpha, etc., etc. For example, if n and q are q prime, if n and q are co-prime, then this has only one term, t equal to 1, and that gives you mu q. Okay, which is what you would expect when you are adding the primitive roots. Okay. Now one needs actually one more sum, which is called the Kloosterman sum. And Ramanujan sum is somewhat a special case of the Kloosterman sum. And this Kloosterman sum is defined by summation A, D, E, A, M plus D, N divided by C. And A is also mod C, And D, of course, I won't say mod C because essentially I also need AD is congruent to. Okay. Therefore, this coefficient of M runs over the residue classes modulo D, and corresponding to the residue classes, the coefficient of L is the inverse of that. Okay. Therefore, this Kloosterman sum is something important. Okay. And now I will give you an example of what we can do with this, all these funny things. I had already written the various things, integral 0 to capital C to infinity, and that had a Ramanujan sum. And then the other one had actually the psi functions. And now let's take the psi functions and then try to simplify that. Since the expressions are so complicated, I cannot remember them there too. Yeah. Therefore, what we had is essentially capital C to C plus capital C. I mean, I'm forgetting the constants. And then you have something like summation D mod C psi of x minus D by C f of D bar by C minus 1 over nx Cx dx by x square. And as this way I was pointing out in a few minutes back, I don't need all those things. I want to know how to do this summation. Therefore, I don't need the dx by x square, I don't need the integral. How do you do the summation? Summation D mod C, psi of x minus D by C, f of D bar by C minus 1 over Cx. Oh, okay. I have to somehow reduce it. Okay. And also, I am only interested in the special case. I am interested only in the special case f of x equal to E and x. Okay, that's the case which I am interested. Even though I proved everything with respect to f, but on the other hand, I am only interested in this. And now, therefore, that summation is congruent to summation D modulo C psi of x minus D by C into f of, which is E of n D bar by C minus n over Cx. I would like to see how one can do such a summation. Okay. The summation is over D, again following the advice of this way, I will forget that, things which are immaterial for us. And now this psi has a Fourier series expansion, and we said that we can use many techniques essentially to make the Fourier series expansion into a finite spot. And therefore, I have to take only one term of the Fourier series expansion and then try to see what happens. Therefore, now one term of this Fourier series expansion will give you summation D modulo C E of x over D divided by C times L divided by L E of n D bar by C. Because I just take the Fourier series expansion for psi, and we have already seen that I can take a finite expression, and therefore I can take one term one by one, and then I can try to sum it up. Okay? And now let me simplify that, and therefore this is equal to summation D modulo C E of XL by C E of minus DL by C divided by L E of ND bar by C. This is what it is. Okay? And now again, things which are not involving DL, let us forget it. And that's a summation which I have to do. This summation is over two variables now, D and L. Now let's simplify that. What do you get? Is a summation over L, 1 over L, summation over D, E of minus L times D plus N times D bar divided by C, D modulo C. Okay? I've just written this part. And now you see this is Kloosterman sum. Okay. Therefore, there is a summation. Two variables are already fixed for you, A and B, for example, and you are running over some C, but this A gets multiplied by C and the B gets multiplied by C bar, and then you have to take mod C. Therefore, any such a sum is called a Kloosterman sum. Okay, which I have already, yeah, any such a sum, that summation E of A M plus N times D divided by C, where AD is congruent to 1 modulo C. M and N are fixed, and A and D go modulo C. Yeah, okay, this such a sum is called the Kloosterman, and that's exactly what you have. And therefore, you need to know how to estimate the Kloosterman sum. And if you have an estimate for the Kloosterman sums, then you can use that estimate, multiply by 1 over L and sum over L. Is it okay? I'm not going to do all the calculations, and the estimate for which mostly we use is a so-called Wales estimate, which tells you that S of M, N, C is bounded by the GCD of M, N, C. There's a C power half, there's a tau C, but I don't think there's any power for the GCD, no? Is there a power for the GCD? There's no power for the GCD. GCD of M and C and Z. I thought yeah. Okay, 1 minute. Let me see whether I have somewhere written. No, I don't think so. That's a. Yeah, exactly. Yeah, tau C is the number of divisors. Yes. Since I was now following Ivanik suddenly, normally I write D of C, but towards you. Okay. Therefore, this is the GCD of M and C times C power half tau C, and that estimate you can put here.
Square root on.
What is that? Yeah. This here for a purpose, because also GCD will be normally very small and won't play a role at all. And that you can put here. And therefore, now you will see, yeah, you can put that estimate here and then simplify and so on and so forth. Okay? This I am not going to do. But on the other hand, always you can reduce it, your integrals, to either Ramanujan sum or Kloosterman sum. And we can do that. Is it okay? Good. Oh, I think it's time to stop. It's a convenient place to stop anyway. Yeah, now next lecture, okay, I'll take 2 minutes. Next lecture, what do we plan to do? And you saw already circle method, and you know the major arc, minor arc, and you also know that this minor arc is of a smaller order than major arc, and therefore you get the representation. But if you are particularly interested in this following problem, n equal to x1 square plus x2 square plus x3 square plus x4 square. And then you should use the standard circle method. It doesn't seem to be easily possible to prove that the minor arc estimate is smaller than the major arc estimate. And therefore, we should do a different circle method, namely the Kloosterman's delta method. Okay? And that circle method gives you an arithmetic formula for that. And that is exactly what we plan to do in the next lecture. Okay, we can stop here.
Any questions? So if not, let's thank Professor Balu for introducing us to so many funny things today. Thank you.